In this lecture, we will talk about negative electrodes for lithium-ion batteries, a crucial component powering our modern electronic devices and electric vehicles. We will explore the fundamental role of the anode, the challenges it faces, and the exciting research pushing the boundaries of this technology. To begin, let's briefly review the basic operation of a lithium-ion batteries. This device is made of four main components: the negative electrode called anode, the positive electrode called cathode, the electrolyte, and the separator. During charge, the cathode material is oxidized and releases lithium ions, which, thanks to the electrolyte, migrate towards the anode. At the same time, the anode material acquires electrons and accommodates lithium ions within its crystalline structure. The electrolyte is an essential component to ensure the migration of lithium ions between the two terminals. Eventually, the positive and negative electrodes are connected by an external circuit, which allows the user to use the energy stored inside the device. During discharge, these reactions are reversed, with the release of lithium ions from the anode to the cathode. Therefore, the anode is where lithium ions and electrons are stored during the charge process. The electrolyte at the solid-liquid interface on the anode side will undergo a series of electrochemical decomposition reactions during the first charge, forming a passivation layer which will prevent any further decomposition reaction. Some lithium is lost during this process, causing a low Coulombic efficiency in the first charge-discharge cycle. This layer is called solid electrolyte interface, and it is of paramount importance for the cycle life of a battery. It can conduct lithium ions but not electrons, thus avoiding any further reduction reaction of the electrolyte. In addition, it is not permeable to the solvent molecule. However, under some circumstances, for instance cell aging and improper cycling condition, the SEI layer can break and further lithium is lost in the next charge. This will lead to a continuous loss of cyclable lithium and thus capacity fading of a cell. The formation of this interface is a complex process which is still the subject of in-depth studies. Anode materials can be divided in three classes according to their reaction mechanism: insertion, conversion, and alloying. All of them have advantages and disadvantages to consider prior to their commercial application in real batteries. Insertion materials are usually characterized by an extremely reversible intercalation reaction accompanied by a low or negligible volume change. They are mainly carbon-based materials, such as graphite, or titanium-based. Anode materials based on conversion mechanism are transition metal compounds, which are reduced during the charge to give metal particles and the corresponding lithium compound. They can offer a higher specific capacity than insertion materials, thanks to the large quantity of exchanged lithium. However, their application is hindered because the stability driven by the structural change of the conversion reaction. Furthermore, they are affected by a large voltage hysteresis which lowers the energy efficiency of the device. On the other hand, alloying materials can store a large amount of lithium compared to the other two classes. They are metals and semi-metals, such as silicon, which can electrochemically form alloys with lithium. However, the alloying reaction is commonly accompanied by a drastic volume change, higher than 200%, which inevitably leads to loss of electrical contact and pulverization of the electrode. Since the first commercialization of lithium-ion batteries in 1991, graphite is the most used anode material. Graphite is a crystalline form of elemental carbon which possesses a unique structure made of parallel graphene layers held together by van der Waals forces. A small interplanar distance of 3.34 angstroms allows graphite to host lithium ions with an intercalation process, with a minimal volume change and a potential close to the lithium redox couple. Lithium intercalation into graphite occurs via a mechanism known as staging. This is a stepwise process in which lithium ions are intercalated in distant layers, leaving a certain gap of unoccupied layers. As the intercalation proceeds, the number of unoccupied layers decreases until reaching the stoichiometry of LiC6. This process is relatively stable and highly reversible, enabling many charge-discharge cycles. Other promising anode materials include the lithium titanium oxide, or LTO, which exhibits excellent cycle stability and safety, but has a lower energy density compared to graphite. LTO is particularly appreciated for applications where safety and long life are fundamental. The formulation of commercial anodes involves optimizing electrode composition, including the active material, usually graphite, LTO, or silicon, a polymer binder such as polyvinylidene difluoride or carboxymethyl cellulose, and a conductive additive like carbon black. These three components are then casted onto copper foils, which act as current collectors. Only in the case of LTO, the current collector can be made of aluminum foils. However, both graphite and LTO have limitations. Their theoretical capacities are relatively low, meaning that they can only store a certain amount of lithium ions per unit mass. This limits the overall energy density and, thus, the autonomy of the battery. The search for increasingly high-performance anode materials has become essential to create batteries with greater energy density. In this regard, researchers are exploring various advanced anode materials. Silicon is a promising candidate due to its high theoretical capacity, which is about 10 times that of graphite. However, silicon undergoes a large volume change during lithiation and delithiation, which can cause cracking and pulverization of the electrode, leading to rapid capacity fade. To address this issue, researchers are developing various strategies, such as the use of nanostructures to mitigate the volume variation, like silicon nanoparticles, nanowires, or composites with carbon materials, or the use of carbon coating or mixtures with graphite. Only in recent years, a small fraction of lithium-ion batteries with silicon anodes have been commercialized. The most important anode materials for the next generation of batteries is lithium metal. Lithium is the lightest metal of the periodic table and has one of the lowest standard redox potential. Furthermore, it has one of the highest theoretical capacities of 3,860 mAh of a gram, making it an attractive anode for electrochemical energy storage systems. Indeed, lithium metal was used in the first battery prototypes by the Nobel Prize Professor Whittingham. However, they were never commercialized because of the safety issues and operational faults. Lithium metal reacts severely with the electrolyte, leading to a short lifespan of the device, as well as safety issues such as dendrite growth, short circuit, and eventually thermal runaway. To mitigate these issues, researchers have explored alternative electrolyte solutions with solid polymer electrolytes, or SPEs, gaining significant attention. Unlike conventional liquid electrolytes, which facilitate uncontrolled lithium deposition and side reactions, SPEs provide a more stable lithium-ion transport environment, reducing the risk of dendrite penetration and improving overall battery safety. Additionally, SPEs eliminate electrolyte leakage, a common issue in a liquid-based system, making them more suitable for long-term and high-energy applications. Various strategies have been explored to optimize their performance, including the incorporation of lithium salts, ceramic fillers, and plasticizers to enhance ion transport and mechanical stability. However, challenges remain, particularly in achieving high ionic conductivity at room temperature and ensuring interfacial compatibility with lithium metal. Advances in materials engineering and electrolyte design are progressively addressing these limitations. SPEs represent a crucial step toward the commercialization of lithium metal batteries, offering a promising pathway for high-performance energy storage in electric vehicles, portable electronic, and grid-scale applications. In addition, challenges remain in terms of cost, scalability, and environmental impact. Further research is needed to develop sustainable and cost-effective anode materials. In the future, we can expect to see the development of novel anode materials with even higher capacities and better performance, enabling the next generation of energy storage devices. In conclusion, anode materials play a critical role in the performance of lithium-ion batteries. While graphite has been the dominant material, advanced materials like silicon offer promising routes for improvement. The ongoing research in this field is essential for meeting the growing demand for high-performance batteries in various applications, from portable electronics to electric vehicles and grid storage.